All right. So the topic for this part is to get to the Larmor formula of dipole radiation for an oscillating or accelerating charge. So we already talked about this, that we can see the power radiated by an electron as surface integral of the flux dA. Okay? And again, I remind that in our previous descriptions here of the macroscopic description often used for light transport, radiative transport in astronomy, the power here and the flux here were typically, say, we took the example of a star where we had the luminosity of this. We do the surface integral of the flux over the area, which for a star that is spherical is just 4 pi FR, the radial flux component, 4 pi, and then the radius of a star squared. This is something that we are very familiar with. It's just a way to make contact to this description here. Now, we also saw before the break that in our case, we can write this as the Poynting vector flux times r squared, magnitude of it, times r squared d omega, where the magnitude of the Poynting vector flux is c divided by 4 pi e squared r squared d omega, where e squared now is our electric field. So now we need to know that from our electron, which it is in our case, as discussed. So, okay, we can look at this emitted power, right? And then if we have an electron here, and now we're going to say that this is static. And we know that all the field lines here, I'm going to just draw them like this, are radial. Yeah? And the electric field is essentially Coulomb's law, which is Q divided by r squared. But if we plug this now in to this formula, then we can see directly that what will happen is that since we're interested in the square, that's the magnitude, we get the 1 over r fourth in the denominator. So this actually then, when you solve it, falls off as 1 over r squared, right? The power emitted. So that means that it falls off extremely quickly, and we wouldn't see light over very large distances. But we do see light over very large distances. We see the galaxies from very, very far away, and so forth. So there is another component here that comes into play when this electron gets accelerated, when it oscillates, when it gets accelerated. Now, one could do this by full solution of the Maxwell's equations and then write it in various ways, where, for example, one way is that you have a second term here to the Coulomb law, which has to do with the second time derivative of the unit vector that's changing, yeah? But the line of sight unit vector, that is changing, okay? So now we're going to try today, though, to actually do it a bit more graphically to see if we can deduce the main points here. So let's say that you had initially your electron there. Then that's going to create the electric field radially outwards. So say at some point out here, we'll go in that direction, here, there, there. My spheres are going to be completely terrible here now, so I encourage you to draw this yourself, because this will be a very poor blackboard drawing for me, with the idea that you're going to have to probably do this yourself. Okay? So now we give this electron a little kick. Okay? And then we'll look at it some time t later. Then it has traveled some delta v times that time t. Okay? Now, from this position then, we can draw the new lines. Okay? So if we look at this now, the parallel line here will be something like this. Okay? Where you have the shell here going down. However, we know that the field lines, they must connect. Okay? So it's like the field lines are dragged away, so that this must connect to this. So outside, if this is now c, speed of light, times t, that is the time afterwards that we're observing this, the delayed time, okay? Then outside that point, the field lines must be undisturbed. They must reflect the position the electron had before we gave it a kick. Because you cannot travel faster than the speed of light here. You do travel with the speed of light, okay? So outside this, they must again be radial, pointing in that direction. Okay? So if you now do the same, for example, here over at this side, you will see that the parallel line goes something like this, and you will have to draw the line something like this. Now, interestingly, in this direction, you won't get anything. Here you will get maximum, but in this direction, of course, you won't get any distortion of the field line because they're going in the same direction. All right? So, what you get then is some sort of tiny sphere, a thin shell here, where your electric field lines are disturbed. And this shell is propagating outwards, of course, according to this, right? And this is now your outward propagating plane wave of radiation. So we can see that as an outward propagating light wave or as a disturbance in the radial electric field. So, okay, can we work out what that disturbance then is? Well, this shell then must be C times delta t, where delta t is the small amount of time that we gave it the kick. Okay? And then we're going to look at, okay, here we have a component in the radial direction, and here we have a component in the call it tangential directions. All right? And then if we have this as a theta, we can work out by just looking at the angles here that the ratio of this must be delta Vt times sine theta divided by ER, which is just the thickness of the shell, which is just C delta T. All right? Now this, we can also then write as the acceleration of the, in this case, the electron, times we have T, but that's a little bit inconvenient, so we're just going to replace that by R divided by C. That's just the speed. So this is just R divided then by C, so C squared, and then we have the sine theta. Now, on large distances now, this, large distances here, is the electric field that will be seen. So this would be then E tangential, which is then ER. Now ER, we know that's just the Coulomb's law. Okay? So that's just then Q, which in this case is just an electron, so I'm just going to write it as an electron. We have E A divided by C squared sine theta, and here comes the whole thing why there are light, why there is light. 1 over R dependence here. In Coulomb's law, we had 1 over R squared. For the static case here, when we put the acceleration onto it, give it a little kick, we end up at large distances with a dependence that is just 1 over R. Okay. Now, let's see what this means. I'm going to save that expression there. I'm going to start up here to look at the power. All right, so we now have the power as the integral here, C divided by 4 squared, and then we have E squared, which now is this. We know that on far distances, we can neglect the Coulomb contribution because it's 1 over R squared, so it falls off as 1 over with that, and the E squared here will fall off as 1 over R squared to the distance, so it will be very, very, very soon negligible, okay? And now, on this hand side, we have E squared, A squared divided by C4, right? And then we have 1 over R squared. Then we have R squared. We have a sine theta d omega. Where, I remind from the last chapter, we know everything about integrating over a solid angle, right? This is just sine theta, d phi, as we know, right? So, and of course, again, I repeat myself, but I think it's worth doing it in this case. Whole thing is that this cancels, so there is no radial dependence on this. All right, what did we get out here? We got A squared, E squared divided by C cubed, then we have a 4 pi, but then of course the phi just comes out as 2 pi as always, and now we had this integral, theta 0 to 2 pi of sine cubed theta d theta, and here was there, you see in the previous class I was already thinking about this integral because I knew I had to solve it after. There is a square missing there. I saw the raised hand. Thank you very much. This one is the one that we can write as our standard mu integral minus 1 to 1, 1 minus mu squared the mu, of course, which hopefully we can integrate now because it's too even, so we don't have this uneven interval. So we get two contributions. The first will just be a 2. The second will just be a 4/3, right? No, 2/3. Isn't it? That's 4/3. So that's 4/3 in the end, which then we have 1/2 there. So it comes out as 2/3 a squared e squared c cubed equals to the power. And this is the Larmor formula for radiation, dipole radiation from an accelerating / oscillating charge. And we're going to use this, like I said, in this chapter. We will use it to analyze the situation where we have an incoming to some electron which is oscillating, and then we get scattering from it, yeah? Where we're going to, again, look at the cross-section is the power. So this is the power then emitted by that electron when it starts to accelerating, yeah? We're also going to use this later on in the course, actually, so I thought I could just hack that. And that is in a situation where, for example, we have an electron coming in here, and then we have, say, a positively charged, so say a proton. Yeah? And then, because of the traction here, we get a little deflection. Now, that deflection corresponds to an acceleration, or deacceleration, in this case, which then it reacts by emitting a photon. This is called free emission or Bremsstrahlung, which we will come to in a later chapter. And we can use the same Larmor formula also there, as we will see. Now, though, I wanted to make some notes about this. First, already, you saw from our or my very poor description, my very poor drawing of the situation here that, you know, when we had an acceleration in this way, there was actually no disturbance of the field line in this direction, right? The maximum was in this direction, as you could deduce, because then the tangential component was just like that, and here was a in between. If you looked at the disturbance, like that, and so forth. So in this here, there won't be any disturbance. And this is what causes this characteristic dipole pattern, right? We could have also looked at this by looking at the differential form, the omega of the Larmor formula, which is then squared a squared c cubed here, and then sine squared of theta, right? And here you can also see, if you look at the power in a given infinitesimal solid angle, when theta is 0, again there is no power. So this is then what draws out this characteristic dipole pattern of radiation here, where you don't have anything emitted in that direction if that is going, but you get maximum in this, and then you get a dipole pattern of radiation like this. And that's because of this effect here, because it's the tangential component that matters. And that tangential component here is 0. I wanted also to make one final comment about this, and that is that, of course, we derived this Larmor formula for a point source, but it is possible to generalize it to a collection of charges. Okay? So if we have such a collection of charges, we can write them as a sum I over all charges Q, which in this case, of course, I wrote directly as the electron. But of course, in general, it's just charge Q, right? And then the radii for each of the particles. So then again, if we take this now, 2 times the time derivative, so d dot dot would just be I qi a I, where this is the acceleration which we have there, right? Now, this is typically called the dipole moment. And in this case, you can see that for such a collection of charges, we could also just write Larmor's formula as 2/3 c cubed d dot dot squared, where d now is the dipole moment. Chart here. Okay. Next, like I said, we will use this now to try to gain some insight into the scattering of light, particularly about the Rayleigh limits, the Thomson limits, and also actually get a first impression, which we'll have to modify a little bit later on, and we'll come to that, of what line scattering really is about. Okay? We will also be able to already now, with the knowledge that we have here and from the previous, do some interesting applications of this, obtaining some sort of estimate for why stars don't become arbitrarily large using the Thomson scattering limit. We will discuss why the sky is blue using the Rayleigh scattering limit, and we will actually have a first thinking about the powerfulness of spectral lines through the Q value of a classical driven damped oscillator. And look why they're so narrow, why they're so powerful. And the convenient way to do that is through this Q value of a classical oscillator, which we'll use together then and also get an impression of the profile function, actually. All right, so that's just a teaser, but this is it for today. I wanted, since we have